So now we're done with the Screen analysis, and we're going to move on to principal components analysis. And this is really a bread and butter technique used across many different fields. It's a really common and ubiquitous method, and for some of you, this will likely be review. I'm sure some of you have seen some principal components analysis before, but it's really important, and it drives some of the other stuff we're going to be doing next week. So we're going to talk about it and go through some of the details, and maybe you'll learn something new, even if you are familiar. So the idea is that when we have a multivariate data set with a bunch of variables, it's possible to extract the same number of orthogonal principal components, where each component represents the maximum shared variability that can be obtained among all of the other variables that's orthogonal to each other principal component. So it's really a way of extracting as much information as you possibly can from the data, and then figuring out how much information is left over and extracting the most from that, and then finding out how much information is left over after that and extracting the most from that until you run out of information to extract. So PCA is a purely data-driven approach. It really just relies on the data set entirely, and it has two goals. It helps us interpret the shared variability among the several variables that are naturally correlated. And so this is the principal components. And then it also helps us identify what's driving this shared variability among correlated variables. I will try to correct that typo in correlated. And so another way to think of this is that the goal is that we are trying to reduce the number of dimensions in our data. So we're trying to think of how we can explain our data in a way that's maybe more parsimonious than we get from the data itself. So to get the principal components, we start by finding the linear combinations of each variable in our data set that will maximize the variability from the output. So we're going to find these coefficients, these A's, such that when we multiply them by our original data and sum up the results, we get a single variable that has the greatest possible variability for any possible coefficients. So based on other stuff we've learned, I imagine you can sort of guess what we're going to do next for how we get the next principal component. So the next thing we're going to do is we're going to do the same thing, and we're going to find another set of coefficients that maximize the variability in our data, except this also has to be uncorrelated with the previous principal component. So it's going to have the highest possible variance we can obtain while also being completely uncorrelated with the first principal component. And so it actually turns out we've learned everything we need to know to get these coefficients and to get even more information about them. Anyone want to stop and think and take a guess as to how we obtain these coefficients based on entirely on stuff that we've already learned in this class? So just to sort of review, we're going to use the eigenvalues and eigenvectors. So their eigenvalues and eigenvectors are ways of representing unique information about square matrices. This is stuff that we've talked about before. These are actually screenshots of previous slides. Eigenvectors will always have k elements, and any k by k matrix will have k perpendicular eigenvectors, and the associated eigenvalues are ways of capturing their proportional lengths, so speaking geometrically. And so if you have, two dimensions, if you have only two variables, you can plot the two different eigenvectors as orthogonal axes at a 90-degree angle that are sort of based on the data. So we can the way the principal components analysis essentially works is we take our data and we move it so that now it's in this new geometric space where the eigenvectors are the axes. So we're transforming our data so that it is in this new eigenvector space. And these new eigenvectors become the new dimensions of our data. And so each successive eigenvector is going to maximize the variability of the data in a given direction, and the eigenvalues tell us how much variability the data has in that direction. So the principal component coefficients, or the component loadings, are just these eigenvectors. the first eigenvector is the first set of coefficients, the second one is the second set of coefficients, so on and so forth. And they can be interpreted as the contributions of each variable to each principal component. And so we order them by the size of the associated eigenvalues from largest to smallest, since each eigenvalue represents the amount of variability accounted for by each principal component. And in fact, we can sum up all of the variances for each variable as the total variance in our data. So this would be the trace of the covariance matrix, and it is also equivalent to the sum of all of the eigenvalues of the covariance matrix. And so that gives us a nice straightforward computation where we take the eigenvalue and divide it by the total variance, and that gives us the proportion of variability accounted for by that principal component. So the eigenvalue associated with the kth principal component divided by the total variance is the amount of variance accounted for by that eigenvalue. So here we're going to look at another simulated example. So this is for simulated data for 400 students who took 6 different classes: statistics, calculus, and physics, composition or writing, English, and literature. And so they got scores of 0 to 100. I left out the means, but the means were around 80. I will try to add that back in. So the means for each one is right around 80. So that's what this simulated data is. So before we run the principal components analysis, we can take a look at the covariance matrix, or the correlation matrix of the data rather, obviously because that's easier to interpret. So we can immediately notice sort of that these first 3 variables are all kind of highly correlated with one another, but they're not as correlated with the next 3, and those next 3 are more correlated with one another though as well. So this gives us a sort of sense of how what the patterns of bivariate correlations are like in the data. What a PCA gives us is the multivariate representation of the shared contributions for each variable to the total variability in the data. So it's a better way of looking at how much multiple variables that are all correlated with one another are sort of correlated with one another, each other are sort of hang together. So one easy way to get the principal component loadings is to just check the eigenvectors. So we can always get the eigenvectors for the covariance matrix, and this will give us the principal component loadings. That's one way to do it. But a slightly nicer output will come from the PRComp function. And so if we print the full output, it'll give us this, but I'm just taking up this rotation object, which is just, it'll give us a little more information if we print the full object. But here the rotation are the principal component loadings, and I'm just doing this so I can round them off. And we can see they're the same magnitudes as these eigenvectors. The first couple are negated just because I think by default it'll make the majority of the first loadings positive, but it doesn't matter. It's just as long as the magnitude sort of or the signs all match up, it's fine. You see that the second principal component, the signs are also flipped. The third one are the same. It doesn't matter as long as the signs are consistent within groupings. And so the way we would sort of read this is we'd look at the first principal component and we'd see, okay, so there's these first 3 variables all have very similar high loadings, and these last 3 have slightly lower, but also similar loading. So we know that the first principal component is really driven mostly by these first 3 variables, and then also similarly by these last 3. And this makes sense since all of the variables were positively correlated with one another. But these first 3 had much higher correlations with one another than they did with the other 3, and they had higher correlations among each other than these did among each other as well. And then the second principal component then is driven much more by this other cluster of the composition, English, and literature. And the first 3 variables also have sort of large negative loadings, which is a function of the fact that much of their shared variability went into this first principal component, and the second one has to be orthogonal. So here we see the second principal component is driven a little bit more by this second group of variables. The summary output will also produce the proportion of total variance accounted for by each component, as well as the cumulative variance and variance accounted for by each component. These are both informative. So here we see the proportion of variance accounted for by the first principal component is 0.49, so almost half the variance in the total variance in the data is accounted for by the first component. The second one accounts for another 35%, and in total, the first two account for about 85%. And then the third principal component only accounts for about 7% in the data, and by that point, we're up to 90-something%. But we can see these last principal components account for a much smaller proportion of the total variance in the data than the first two. And so this is sort of that interpretation I gave before, just written down for reference. So another thing we can do is we can actually extract the components themselves. So this is the coefficients multiplied by the original data. So this is the first principal component. This actually has 400 rows, which is the number of rows in the original data. I'm just putting the first 6 here. This is the second principal component, the third principal component, so on and so forth. We can also check the correlations between each principal component and the original data. So here we see each of the variables is reasonably highly correlated with the first principal component. But once again, the first three variables have higher correlations, and the second not also high, but not quite so high. And then it's sort of flipped here for the second principal component. We have negative correlations for the first three, and then higher positive correlations for the last three. Then we also notice that these correlations become quite a bit smaller as we go. So like they're even, as soon as we get to the third principal component, this 0.43 is smaller than any of the correlations for the first two principal components. And so the interpretation here is similar again, and so this just goes over sort of what I just said. And so we also now kind of get to this idea that we want to decide which components we want to interpret. And so really I've focused on the first two components so far, and there's a reason for that. We could continue interpreting additional components, but why might we not want to? And the reason is that combined, the first two components account for such a large proportion of the total variance in the data, by far the lion's share. And so this is sort of the second goal of principal components analysis, figuring out how we can account for as much of the variability as possible with as few components as possible. This is also called dimensionality reduction. And so assessing the total variability accounted for is one method. This is a heuristic method for dimensionality reduction. We say it's a heuristic method because there isn't really like a rule. There's not like a hard cut line where you say this is where I decide to stop interpreting components. But we can make pretty informed decisions based on the data and based on the results. And so another way to look at this is visually. So we can do a Scree plot. So what a Scree plot does is it plots the total variability accounted for by each successive component. And what we're looking for is a sort of bend or elbow in the plot. And this tells us that the remaining components don't really differ in how much variability they account for. And we may not want to interpret them in this case. So here's a Scree plot. This is a default Scree plot function in R. So here we see clearly there's an elbow in the plot here. And so here the y-axis is the total variance. This is a kind of weird scale. It's difficult to interpret. It doesn't really matter so much what the scale is. What really matters is we're looking for the pattern where there's a large drop in the amount of variability accounted for by each successive component, then suddenly it flattens out. So these last few components are not explaining much more variability than any other components, while these first two are explaining quite a bit more than the rest. So here's a slightly nicer Scree plot from the psych package. This one, you enter the data, and here I'm setting factors to false because that is for factor analysis, which we will go over next week. This is, kind of a nicer looking one. And this one on the y-axis, we have the eigenvalues as rather than the total variance, but you note that the plot is the same. It's just a different scale. Okay, this slide got a little bit cut off. I will fix that. I didn't realize the slide was cut off that way. Anyway, so a more principled approach to selecting how many components we want to interpret is called parallel analysis. And the idea here is that what we're going to do is we're going to repeatedly just randomly generate a data set of the same size as our original data. And then we're going to estimate the amount of variance accounted for by each principal component. So then you average the results for each of those simulated data sets, and you compare the eigenvalues from the covariance of your original data to the average eigenvalues of the simulated data. And so any principal components from your actual data that have higher eigenvalues than the average ones from the simulated data can be seen as capturing more variability than one would expect by chance. And so we can look at these on a Scree plot to sort of get an idea what they look like. And the ones that are going to, so the ones that are accounting for more variability than you'd expect by chance are the ones you definitely want to interpret. So here is an example of the Scree plot with the parallel analysis using the FA parallel function from the Scree, the psych package. And so here we see this red line represents the simulated data. And so we want to see how many principal components are above that red line. So these first two are above that red line, meaning that these eigenvalues are larger than we would expect by chance alone. And then these ones that are below, these are not larger than what we would expect by chance alone. So this sort of suggests that we wouldn't want to interpret these. These could just be capturing noise. And so this just reiterates what I just said, but then sort of one additional question. If we look at this plot, we do see that the red line actually has a downward slope. And so why would that be if this is based on purely random data? It suggests that different components have different amounts of information. And why would that be true just from random data alone? And the reason is that this is just what happens when you fit any kind of analysis like this on finite samples. Each simulated data set is finite, so just by chance alone, some of the eigenvalues are going to be different sizes, and so you're always going to order them by size. There's always going to be some slightly larger eigenvalues in every simulated data set. This is sort of I find it to be a really great representation of what is happening with overfit. And so this is also why we can't just compare our results to uniform principal components where each principal component is just exactly the same value. We actually do need to compare to what we would expect by chance alone, because we would expect by chance alone that certain eigenvalues would be slightly larger than others. And here's just some code that makes a slightly nicer Scree plot. So this is based on very similar to something that we did for a paper that I just think it is more publishable and looks a bit nicer. It's done with ggplot by extracting some of the elements from the parallel analysis that I did before. So the para here is PARA I saved the parallel analysis information into an object, and here I'm just extracting it and I'm putting it into a slightly nicer looking plot.